In this video, we will combine the equilibrium constant with the ice table in order to calculate any of the required values in an equilibrium calculation. In the first type of example, we will calculate equilibrium concentration if we are given a Kc value and an initial reactant concentration. Now for this example, it will be for a simple homogeneous system where all the species are in gaseous form. So our example deals with the production of hydrogen from carbon monoxide and water. We are told that at equilibrium, the constant is 0.83 at 700 Kelvin, and that we start with 1 mole of CO and 1 mole of water vapor in a 5-liter container. And we're asked to find what amount of each substance will be present at equilibrium. This slide just summarizes the information we're required to find, which is the amount in moles of the carbon monoxide, water vapor, hydrogen gas, and carbon dioxide at equilibrium. We're given the balanced chemical equation as well as the initial amount of each gas. The volume of the container, which will be important because we need to determine the concentration of each species, and then the equilibrium constant as well. Now remember, in our ice tables, we have to use concentration values, not amounts. So therefore, the very first step we're going to do in any equation, any example, is to determine the concentration of each species. We're told we have 1 mole of the carbon monoxide and water vapor. The first thing we need to do then is to divide by 5 liters, which is the size of the container, to determine the concentration of carbon monoxide and water is actually 0.20 moles per liter. So now we have the concentration of the reactants. We can now put those values into our table. So that is 0.2 and 0.2. Now remember, in your ice table, I encourage you to put in the coefficient of the balanced equation as well. Luckily for us, all the coefficient here are the 1s, so therefore it doesn't affect our stoichiometry. And then the next step is to let the change in the molar concentration be x. So carbon monoxide, you will be reduced by whatever gets reacted, so it's negative x. Similarly for water vapor. However, for hydrogen gas, it will be a positive amount, as well as for carbon monoxide. Next, we can do the math. At equilibrium, it will be 0.2 minus x for carbon monoxide. For water vapor, again, it will be 0.2 minus x. For hydrogen gas, it will be x. And for carbon dioxide, it will just be x. This slide set just reminds us that the changes in the concentration of the reactants will be negative because they are being used up in the reaction, but the change in the concentration of the products is positive because they are being produced. Our next step is to set up our equilibrium expression. Remember, an equilibration expression is a concentration of the products divided by the concentration of the reactants. And luckily for us, the coefficients are 1, therefore the powers or the exponents here are also 1 as well. And they will remain an invisible 1 in order to simplify our math. Our next step is to substitute in all our known values. We are told that the equilibrium constant is 0.83. And in our ice table, we just figured out the equilibrium concentration of hydrogen, carbon dioxide, carbon monoxide, and water vapor, so we substitute those values appropriately. Next, we simplified. X times x is now x squared, and 0.2 minus x times 0.2 minus x is merely 0.2 minus x squared. In order to get rid of the square, we square root both sides, so therefore the left-hand side is now 0.9110, and the right-hand side is just x divided by 0.2 minus x. Now we rearrange our equation and then solve for x, so that we find x is 0.09534 moles per liter. Once we have figured the value of x, we can now go back and replace that value in our ice table. So now negative x is just merely negative 0.095. So then our final equilibrium concentration for carbon monoxide is 0.105 moles per liter. For water vapor, it's the same. For hydrogen gas, the concentration is X, or 0.095 moles per liter, and same for carbon dioxide. Lastly, since we're asked to find the amount, or the moles, of each chemical species, we now have to multiply by the volume of a container, which is 5 liters, to determine the total amount. So therefore, the amount of hydrogen gas and carbon dioxide is 0.48 moles, and the amount of carbon monoxide and the amount of water vapor is 0.5 moles. And as a final step, we can double check our work. We see that products are in the numerator in our equilibrium expression, and the reactants are a denominator. The concentration is in moles per liter, and lastly, we could substitute those concentration values into our equilibrium expression, and we should get our equilibrium constant, Kc. In your textbook is a similar problem. However, for this question, the conditions are now at 900 degrees Celsius. And as you remember, if the temperature changes, so will the equilibrium constant. So now the equilibrium constant is 4.20. In this question, you're given a 500 milliliter stainless steel container, or half a liter container, and you're starting with 2 moles of each reactant. Therefore, the concentration of carbon monoxide and the concentration of water vapor is now 4 moles per liter. So now we input our findings from our previous slide into our ice table. So again, we have 4 moles per liter of carbon dioxide as well as water vapor. Again, we're going to put in negative X as the amount of carbon monoxide we're going to lose, and same as for water. The amount of carbon dioxide we're going to gain will be positive X, and same for hydrogen gas. And again, because the coefficient for this balanced equation is our invisible 1, all of the values are just 1. There is no need to do stoichiometry here. And now we do our math. So then the equilibrium concentration for carbon monoxide is 4 minus X, same for water, and X for carbon dioxide and hydrogen gas. The next step, we take our equilibrium values for all the reactants, all the end products, we put it into our equilibrium expression. And then when we simplify, we have the square root of 4.20, which is 2.05, equals X divided by 4 minus X. Rearranging for math, we find that the final answer, X, is 2.69. And as the final step, we go back into our ice table. We replace X with 2.69 to find our final equilibrium concentration of all the species. And we have solved our equilibrium example. So as a final conclusion, a couple of pointers to remember. First, in our ice table, we have to put in concentration values, so that if we're given an amount, we have to divide by the total volume of a container to find concentration. And second, we have to keep in mind of any stoichiometry ratio when we do our change rho. As well, if the coefficient in the balanced chemical equation is not 1, you may also have exponential powers to deal with in your equilibrium expression.